Okay. So I myself, I also looked at the footprint of the different simulations. Like I downloaded those images too, Rachel, that I was just like trying to get an idea of what they're doing and like if it makes sense, like what we're getting from the microrealism metrics and also the metrics that I was testing on them. And I also wanted to mention, like, Rachel, you know that like Fed and her group, they have this like this set of Hill pixels for the whole galactic plane. And they were also like interested to know like what are the other parts of the plane, like a smaller parts of the plane that are more interesting for other science cases, things like that. So yes, I've already worked on like their set of Hill pixels, and like I have run the metrics on that. So then maybe we can also discuss like on how we want to like go ahead and maybe like change that, like decrease, like reduce it to make it into like a specific part of the plane, something like that. Yeah, and yeah, that's pretty much what I wanted to say. Is there anything else on the cadence notes? All right. If not, so I guess we can get started with Mark and Tristan's presentation. Thank you so much. Oh yeah, Tristan, yeah. Please go ahead.
Yes, I will share my screen. So, do you see my screen? Yes. Okay. Okay. So, well, I'll be. It will be a quick presentation because it's not directly related to the cadencing, but so I will present you my work on the about search of intermediate mass black hole using gravitational microlensing. So the thing is that so you know that we can use the microlensing effect to detect compact objects in the galactic halo if we look towards the Large Machine Cloud, for example. And that is, it was, so microlensing surveys has been used to constrain the halo mass fraction in the form of compact objects. Here I plotted I show you the constraint put by Ogle in black and the EROS experiment in blue. So the surveys put constraint up to several tens of solar masses. But as you know, a few years ago, merger of black hole of several tens of solar masses up to well, recently 150 solar masses have been detected using gravitational waves. So it has renewed the interest in looking for dark matter as compact objects, so primordial black holes. And the thing is, we need longer surveys to be able to study objects that are heavier than 10 solar masses. And the idea of this work was to combine existing survey rather than waiting for longer surveys. So here in the bottom plot, I show you the duration of the different surveys that was done and that will be done towards the LMC. And as you can see, we can have a very long. We could have very long light curve if we had all the data combined. But I only have access to the mature and EROS data, so this is what I used for my work. So here I will present you briefly what are EROS and mature. So
Rachel has a question.
Yes.
Thanks. Did you know that the MOA data have recently been released?
I don't think so.
They have. They should now be available through the IPAC archive.
Okay.
This was negotiated quite recently, but that might be something to look into.
So is this
yes.
all of the data?
The field is very small.
Non-events?
I think the field, their field was very small in the past. I don't know now. If
It's much larger now, so
Okay.
it would be worth exploring
Yes.
anyway.
I didn't know. Yes. Okay. So yes, so well, I use the EROS and the Metro data. So here are the scale coverage of the two experiments, Metro in orange and the EROS in gray. Metro was well, had a bit smaller field, but they were looking for fainter stars. So I combined the catalogs and I obtained 12.5 million light years with total duration of 10.6 years, with a bit of overlap between EROS and Metro, which is always good to see if we have the same light curve modification in both surveys. So with they were observed with 4 different non-standard filters, 2 for each survey, and they have between a few hundreds and a few thousand total measurement points. So the microsync, this microsync search is based on a systematic fitting of a microsync effect, an either light curve and a flat light curve to compare the two. And the main selection cut are based on these two fits. So if the microsync fit is good and if the microsync fit is better than the flat light curve fit, which is quantified by this delta k squared. So this is so there are also several other cuts. I will not detail them, but to remove physical background, for example, light echo from supernova 1987A or AGN. Like for example here, I have at the bottom. I have an example of a light curve from an active galactic nuclei in EROS and Metro. Well, the most important is that we did not detect any convincing microsync candidates at the end of the analysis. So, to put constraints, we need to know the actual number of stars we survey, the actual number of stars that could undergo a microsync effect. So we need to take into account blending, and we took it into account by comparing our catalogs and HST images that were in the same fields. There are a few HST images that are in the common fields of EROS and Metro. And we looked at the nearby stars in SST from EROS Metro source and estimated their blend factors. And we did for now we did this for 2 different stellar densities. So we have blending distribution for low stellar density and high stellar density. Well. We also estimated the fraction of binary source stars using Gaia because HST is not able to separate stars that are closer than 0.5 arcsecond. And if the distribution of stars in HST is uniform, but maybe for very small angular separation, we could have well, binary stars that could already add really increase our blending. So we used Gaia to see if this was a problem, and we found out that so we studied nearby stars nearby from the sun in Gaia, and we extrapolated the result in the LMC. And we observed that less than 3% of binary stars are separated by by more than 2 astronomical units, which is the Einstein radius projected in the LMC for a length of a mass of 100 solar masses. So it should not. So binary sources should not be a problem for blending in our case. And so, as I said, yes, to put the constraint, we need to estimate the number of expected macro-lensing events. If we had a halo of a certain composed of a certain fraction of compact objects. So to do this, I simulated macro-lensing effect well, on the Eros-Macho light curve using lenses from a spherical isothermal halo with a direct mass distribution, so for different masses, and using the blending coefficient that we obtain by comparing with the H50 images. I also took into account the efficiency loss from parallax because as we look for very long timescale event, parallax could have been a real problem, but we found that it was really negligible, at least for Eros and Macho, because the ARPA are not very good. And I also took into account the efficiency loss from binary lenses because we are not sensible for sensitive to this kind of effects, and also the fact that we have incorrectly matched stars because astrometry from Macho was not very good. So was not very good. So we have some stars that are incorrectly matched between Eros and Macho. And we also have some duplicates because Macho had a lot of overlap between fields. So we obtain those constraints in black for the halo mass fraction composed of compact objects. I also plotted the constraint from past macro-lensing surveys. And as you can see, we have really put new, we really have constraints for lenses of 100 solar masses and more, so a few hundred of solar masses, which would not be possible with only one of the surveys. So it really shows again we have combining the survey. So this is a conservative estimate. We still have to refine our cuts, our selection cuts. We can gain quite a bit of efficiency. We also plan to use the union of the two catalog because so until now I only use the stars that had measurement in the two catalogs, but if we add all the stars, we can gain a bit of efficiency. Maybe not that much, but it is a thing to do. And of course, adding more data would be really good. For example, Supermacho or Huggle, but well, maybe more if the data is available. And regarding LSST, as the duration of LSST will be of 10 years, which is roughly what the total duration of our combined catalog is. It should be able to be sensitive to the same mass range, but well, with far better constraint because it has a really good photometric precision. So, well, that's it. If you have any questions, don't hesitate. Yes.
I think there was a paper about the microlensing threshold and cut you had from Kepler data. I think Kim Gries published something about that a couple of years ago. Do you know how your results compare with that? I think he's probing, or they're probing the same parameter space.
From which experiment?
That was a Kepler satellite, and
Kepler.
because the absence of microlensing events and the respective number of Kepler light curves, they draw some conclusion on the limits of massive compact halo objects. There's a FISREF article, I think. Let me check that. But okay, no, but I can send that later to you.
Lensing,
okay.
it's a different paper, you say.
Yeah.
Okay.
It's a different survey. They just became from the Kepler data itself, which is a bit surprising. They were able to put some constraints, which I found interesting. So I was just wondering if you're aware of that. If not, no problem. Thanks very much.
I didn't see it. Yes.
It's because of their excellent photometric resolution, I suppose. Yeah.
Okay.
Okay. I should check.
But if you have the reference, yes, you can send it to me.
You know, it's interesting though, because with Kepler, I haven't read Kim's paper, so that's the first thing to do, I suppose. But one of the problems, I thought we would find microlensing there too. But one of the problems is that as they go through different quarters, there would be a kind of a shift. So many microlensing events should continue over a quarter, but it would be very hard to actually detect them. You know, so where Kepler helps you is because it has such good photometry that you can see really low magnification events at high confidence, but a low magnification event that takes a while, it just seemed to get broken up into pieces that made it hard to compare. So unlike where you're looking at transits or peaks of events where things change quickly and the relative photometry over short times is amazing with Kepler, the longer time following was rather difficult. So I wonder how they were able to place limits. You know, a big job to actually look for lensing in the Kepler data.
I've posted the link. I'm trying to get the article, but I need to go through to our institute VPN. So that is currently broken for some reason. So I can comment on that next week or so.
There is some hope to use also the data from SuperMacho. Unfortunately, it was not possible until now for bureaucratic issues, I think. But Chris Stubbs, we pushed for this for us to get the data from SuperMacho. So we should push again, because as you see, well, the gain is interesting. You know, it's the same data, same sample of data. Just put the light curves, join the light curves, and then you have a really significant increase in efficiency, because as mentioned Tristan, if he adds the unions, I mean the light curves that are not part of this intersection, instead of waiting for 8 or 9 events, we will expect maybe 1 more events, not more, because of the too short survey of each experiment. So this pretty okay. That was a challenge at the beginning of his PhD thesis, and it's interesting to see that it seems to work.
I see another question.
Yeah, if you could go back to the slide you had about the procedure, the one with the flowchart. I noticed on the right-hand side here, after you fitted the parameters, you had 116 events. And then you have a section that says source star not in the sparse region of the color magnitude diagram, which does rather down select a lot of your candidates.
Yes, in this case, I selected only the sources that were in the part where you have 99% 90% of your sources in the color match diagram. But in fact, this selection can be, this cut can be relaxed. So you can increase the efficiency without reducing its the number of events you remove. So yes, there is quite a lot. Well, there is some light curves. There are some light curves from stars that are very red or very red or very blue, which show some variations. Very long timescale variations that looks a bit like microlensing. Usually there is some other variations, smaller variation on the light curve. So even if there is no, right, maybe we could use another type of section cut to remove them.
Yeah,
I wonder if that could bring back, because you're losing candidates quite early on in your filtering process, and I wondered if that could maybe be used to bring back some events that are maybe not quite meeting your selection thresholds yet.
Yes.
You know, the point is that in this some of the sparse regions, you have, for example, for the supergiant, red supergiant, you have an accumulation of very long, very long periodic miracity, probably. So that's one of the main physical background. That was the historical reason for this type of cut, but it will be refined, yeah.
Yeah.
And also the fact that if we only have one event that is in the very unlikely zone of the color match diagram, it can be also a bit difficult to say this is microlensing.
I guess one thing that you could also do is turn the problem on its head and use the long-term LSST data to exclude the MIRAs and filter out everything that you know not to be microlensing in future.
Sure.
Yes.
Right.
But then also you have the potential for lensing of variable stars. So the two phenomena are conflated.
Yes.
Yep.
Okay. If there is no more question, I think we can finish here.
Well, thank you very much for that talk, Tristan.
Yeah.
Do you mind if we
Thank you so
post the
much.
recording to the TVS website?
no.
Because I'm
You-
sure lots of people will be interested.
Yes, you can.
Thank you.
No problems.
Samaya, just on the logistics grounds, you're running this recording, so could you upload that talk for me and I'll put it on the website?
Sure, yeah,
Great,
of course.
thank you.
Oh, you're welcome. Great. That was a really nice talk. Really interesting. So is there anything else at this point that we want to discuss? I believe, Rachel, you sent out an email about tomorrow's TVS meeting that you asked that people who are preparing cadence notes prepare a single slide for their cadence notes and present it tomorrow, right? Yeah. Okay. So so just keep that in mind if you're writing a cadence notes. Just prepare that a slide and present it. Yeah.
Just by the way, I just remember one detail in Tristan's studies. He shows the efficiency as a function of the time of maximum magnification, and he shows, I think you have this in one of your plots, Tristan. He shows that there is no loss of efficiency during interseasonal time,
Yes.
for the long time scale events only. So that would be an interesting input for the LSST to argue on the maximum LSST hold that we could support with, that we could not support. It's a French word, je trouve plus mon mot, that we could accept or tolerate before starting to lose it. So that's maybe we should make a point about this distribution in another session.
Yeah.
Because this is real data, and then you have the real holds, the real defects of sampling, and you have the real interseasonal gap, and that's, I think you could probably easily produce a distribution showing the impact of this gap as a function of the Einstein duration. And this can be a very good input for the limitation, for the very good input for the cadencing.
I think we do have some metrics regarding limiting the gap in light curves already, but it's a question of how well they're being applied. It's
For a long
not
time,
clear to me that they are.
for a long time scale.
Yes, yeah.
Okay.
But specifically for any observations that are taking place in the Roman survey footprint, because that was the context they were proposed in. I don't know if they're being applied generally to the rest of the Milky Way.
Right. Anyway, yes,
I think it's possible to test it for like, I mean, for different surveys and like different parts of the sky. That's like flexible for in that aspect.
Mm. It's something we need to think about in terms of the figures of merit, because I can see some trade-offs might end up having to be made over the region that we cover with how long we cover it, and whether we implement a rolling cadence, which would potentially introduce some very long timescale gaps of maybe a couple of years, but then come back to the field later on. And that's the sort of science that we'll lose out from if that strategy is adopted.
Yeah.
So
that will be probably bad for the long time scale. Yeah.
yes, and I think that is something that we definitely need to make sure is captured in our figures of merit. I'm not sure that we are doing that at the moment. I think we have the metrics. I just think they're not yet being applied in figures of merit. That's something to think about.
A figure coming from this type of analysis is like also is equivalent to also a metrics. You know, that's a general metrics. Okay, it's according to a low photometric resolution experiment, but maybe we can tune some with a little effort. We may be able to adapt this.
I think it is possibly worth considering a separate cadence note to make that point, because cadence notes have to be by definition very short, and it would help if they are self-contained self-contained points to make these long timescale events, which I suspect are going to sort of come into a different category. So far, the math team have kind of assumed that anything that is extremely long timescale will just naturally come out of the data. And depending on the strategy, it's not clear to me that that's true.
Yeah, okay. So I started to modify a little bit well, I have just play into the cadence document in the overleaf on the microlensing.tech. So maybe it could be a good place where to start something on this. Okay.
Yeah. We can definitely discuss that, whether or not we want to like add that to this current like cadence notes for microlensing detection, or like if it's better like to add one for like a longer events.
Yeah.
We can
Perhaps
definitely discuss that. Yeah.
I think it's worth getting text down in the overleaf document, and then we'll work out how to arrange it, maybe separate it later. Okay, I'm afraid I have to go to another meeting, but
Yeah.
Yeah.
thanks everybody,
Sure.
and Tristan especially.
Yeah.
Bye.
Thank
you.
you.
Very interesting.
See you
Bye.
next time.
Bye-bye. So
Everybody leaves.